Hi there, Mr. Sutton here, bringing you the BC Calculus 7-7 Part 1 homework solutions on geometric, nth term, and ratio tests. To see if this series converges or diverges, we always start with the nth term test. So taking the limit of this nth term, we've basically got plus or minus, this is really just n over n if you ignore these slower growing terms. So this is really just going to be plus or minus 1 then. Significantly, this is not 0. So this one fails the nth term test and diverges. On this problem, I'm trying to figure out whether this series converges. To make my life a little bit easier, and I'm about to take the nth term test here, I'm going to turn this into n factorial over e to the n. So now if I take the limit of that expression as n approaches infinity, I see that I've got n factorial, which is a faster growing function than exponential growth, in the numerator. That means this is going to infinity, since it's top-heavy. Since it's not a zero limit, that means that this fails the nth term test and is going to keep growing without bound, so we would say this diverges. For this problem, we're trying to see if this series converges. I'm going to try the nth term test first, so let me take the limit of this whole thing as n approaches infinity. And as n approaches infinity, this slower growing term of -1 is going to go away. We've essentially got the square root of 4n squared, which is just 2n, if we simplify it. And then I can just reduce this to 1/2. Now the important piece here is that this does not equal 0. Because it does not equal 0, because our nth term is not getting infinitely small, that means that this is just going to keep growing and we have a diverging series by the nth term test. For this problem, we want the sum of this infinite geometric series. So for that, we need the a1 value and the common ratio, r. a1 is just this 3/2 term, the first term. For the common ratio, I need to do one term divided by the term before it. So 9/16 over 3/2 should give us that. Same change flip, we've got 9 over 16 times 2/3. So this is going to be, let's see here, 2 and 16 cancel to give me 1 over 8. 9 and 3, that gives me 3 up top. So 3 over 8 when the dust settles. Now in this problem, they didn't have an option for diverging, but let me just check to see if this converges just for the sake of doing it here. My common ratio absolute value is 3/8, and that is less than 1. So we know for sure that this is going to converge. So let's see what it converges to. I need my infinite sum formula, a1 over 1 minus r. This is going to be 3/2 over 1 minus 3/8. So 3/2 over 5/8. Same change flip, we've got 3/2 times 8/5. And normally I would reduce, but I'm not going to on this one, and you'll see why. So this is 24 over 10 initially. And the reason I left it with a 10 down here and didn't reduce it is because 10 is really easy to divide by. 24 over 10, that's just 2.4, which I needed to do without a calculator to match answer choice C. On this problem, we have this series of sine squared of x, all of that to the k, and they want to know if we do f of 1, what's going to happen with all this. So let me just rewrite this with 1 plugged in for x. This is essentially sine squared of 1 to the k power. Now, for them to ask us to add this infinite series together, that means this must be either a geometric or some other special kind of thing. It is geometric. We're doing the same thing multiplied by itself over and over again with this k power. So since it's geometric, I need to figure out the a1 and the r values. a1 is just going to be what I get when I plug in 1 for k. That's just going to be sine squared of 1. The r value is the thing we keep multiplying by over and over again, which also happens to be sine squared of 1. So let me just double check to make sure this does converge by using the absolute value of my common ratio. So my absolute value of my common ratio is just sine squared of 1. Since sine is, let's see, since sine of pi over 2 would be 1, sine of 1 is going to be something that's less than 1, and if I square that, I have something else that's less than 1. Since this is all less than 1, that means we converge for this one. So let me actually go ahead and plug all this information into my infinite sum formula now. That's a1 over 1 minus r. So that's going to be sine squared over 1, sine squared of 1 divided by 1 minus sine squared of 1. There might be a fancier way to do this, but it's a calculator question, so I'm actually just going to plug this into the calculator now. So here's what this looks like on the calculator. To do sine squared of 1, I need to do sine of 1 and then square all of that. Same thing in the denominator. And that's going to come out to about 2.426, which is going to give me answer choice D. On this problem, we have this infinite series with a nth partial sum of -1 to the n plus 1. We want the sum of the series from 1 to infinity. Okay, well, let's see what happens if we keep plugging in bigger and bigger n values. So let's say I have just an n value of 1. That's going to be -1 to the 2, which is just 1. If I have -1 to the 3, which is what I get if I have n equals 2, well, that's just -1. If I have an n value of 3, this goes back to +1. So you can see this is just going to keep alternating back and forth between negative and +1. Since my sum keeps alternating back and forth between two numbers and can't really decide on which one, this is going to diverge by oscillation, which means that we just pick answer choice E, the series diverges. On this problem, we're given S of n equals this crazy fraction combination. We want to know what number this sequence, this is just a sequence, converges to. Okay, so we're just going to take the limit as n approaches infinity of this thing, and while I'm doing this, I'm also going to reduce a little bit. I see that I have a 5 to the n and a 5 to the n plus 1. Since I have the same base, I can divide those together and subtract the exponents. That'll just give me a 5 in the denominator, and this 5 to the n is gone. So I have limit as n approaches infinity of 5 plus n quantity to the 100th over 5 times 4 plus n to the 100th. And now, if I just imagine what's going to happen when I multiply things out here, or actually, here's what we can do. Ignore the slower growing terms inside this 100th power. So I'm going to ignore this 5, I'm going to ignore this 4. We just have n to the 100th. We have an n to the 100th down here, but we also had this 5 out in front. So that's going to count. Multiplication counts. This little addition by 4 does not. So we have n to the 100th over 5n to the 100th, which just reduces to 1/5, giving me answer choice A. On this problem, we're asked to consider this infinite series with an initial value of 16, and we said, let's see, a of n plus 1 over a sub n equals 1/2. They want the sum of the series. Well, when they're asking for the sum of a series that's infinite, that's a big tip-off that it's probably a geometric series, and in fact, this a over a business, this is talking about the common ratio. This is the n plus 1th term over the nth term, and they're saying that that's a constant value of 1/2. So to summarize, we have a geometric series, since we have a common ratio here that doesn't change. We have an a1 value of 16. They gave us that. This is the r value, essentially. And they have an option for this thing diverging, so let's check to see if it actually converges. Since my r value, absolute value, is 1/2, and this is less than 1, that means this geometric series will converge. So let's go ahead and find out what it converges to. My infinite sum formula is a1 over 1 minus r. So I can write this as 16 over 1 minus 1/2. Well, this is just 16 over 1/2, which is just going to be 32 if I multiply by 2, multiply by the reciprocal. So that gives me choice D. For this problem, I want the sum of this series, and they have an option for the series diverging, so I have to check to see that this actually converges at all before I waste my time figuring it out. Now the key on this one, since they're asking for a sum, is realizing it's probably a geometric series. I can get it more geometric looking if I split this e term here up into e to the n times e. And now I can just rewrite this as one big fraction, -2 over e, all raised to the nth power. And we still have 1 over e out there. So this is geometric. We have something that we're repeating with multiplication. So let me write out my terms here. My a1, my initial value, that's going to be what I get when I plug in 1 for n. That's going to be 1 over e times -2 over e, which would be -2 over e squared. So that's our A1. That's going to be fun to deal with if we have to add this thing together. Our common ratio is just this exponential base that keeps getting multiplied by, so negative 2 over e. Now, checking for convergence, the absolute value of my common ratio is going to be positive 2 over e. Is that greater than or less than or equal to 1, or which of these situations? The key on this one, and this was a no calculator question, you have to realize that e is bigger than 2. E is about 2.7 and some change. So 2 divided by something bigger than 2 is going to be less than 1, which means this does actually converge, and we have to add it together. So let's break out the infinite sum formula, a1 over 1 minus r. So this is going to be negative 2 over e squared in the numerator, and 1 plus 2 over e in the denominator. This, of course, matches none of the answer choices. They're going to make us simplify. So let's do that. In the denominator down here, we have this 1 plus 2 over e. I want to turn that in just to one fraction so I can more easily divide the numerator by this stuff. So getting a common denominator down here, this is really e over e plus 2 over e. So that's just e plus 2 over e. And now a little same change flip magic. I've got negative 2 over e squared times e over e plus 2. The e's are going to cancel, at least partially. I'm going to have a negative 2 in the numerator. In the denominator, I've got e times e plus 2, or e squared plus 2e, if I distribute that out. And that's going to match answer choice B, right over there.